This is a concluding video on our chapter 2 on course Laser Physics, and the topic of today's lecture is saturation and gain. So essentially I will be showing you the mathematics that shows that when we have absorption processes and also stimulated emission processes, so essentially gain inside the material, we start having saturation effects, and that can really very fundamentally move or change the laser behavior. So that's why we are introducing them. And also we are able to connect the previous discussion regarding homogeneous and inhomogeneous line broadening mechanisms within the kind of saturation effects. So we are showing you what are phenomena known as spectral hole burning processes. So these are basically the main things we want to show to you: saturation effects and a little bit more about the line broadening mechanisms and their implications on lasing. So let's get started. We, as always, start some assumptions and mathematics. So let's go by assuming that we have reached a steady state condition within our two-level system. So this basically just means that the population of interest, so the population of the ground state, Ng, and then also the population of the excited state, Ne, are now time-independent variables. So basically, we assume that we are under steady state so that these populations don't change anymore. That's the meaning of steady state condition. Let's now consider what happens. We are keeping an incident photon flux hitting the material, so F is really affecting still the absorption. And if we are looking at the kind of like differential change in the absorption, we can write that this is this kind of term here. So what this basically physically means that we have incident photon flux, and we want to understand how the photon flux is being changed due to absorption. We can write it into this kind of terms. So we have the absorption cross-section, we have the population of the ground state, we have the incident photon flux, and then we have this like a differential length of our gain media. So this is how absorption takes place and how it changes the photon flux. The minus sign here, of course, signifies that the absorption is loss for the field. Similarly, we can write a same kind of term corresponding to stimulated emission process. So now we have a change in the photon flux due to stimulated emission. So we have this subindex ST, stimulated emission, there. And this is a kind of similar looking term, but now we have plus sign here and we have the population of the excited state, but otherwise it looks exactly the same kind of term. Here, plus sign signifies emission, so essentially gain for the field into this frequency. Okay. Now, the change of the total flux, of course, is the sum of these two processes. So the total change of photon flux, dF, can be written to be that it's the sum of these differential changes. So we can write everything together. So we have minus sigma, and then inside the parentheses, we have the population difference times F, the photon flux, times dz. And we can really integrate this quickly to understand how the photon flux evolves as a function of propagation distance z. So this is basically of the form that we have the original photon flux, for example, hitting the gain medium at z equals 0 plane, and then we have this kind of exponential term, my exponent minus sigma, population difference times z. So either we can have an exponentially decaying photon flux or exponentially large expanding photon flux, increasing photon flux. And let's consider these two different steady state scenarios. So in the first case, if we do have a case where we have a larger population at the ground state than in the excited state, then we have a case that the photon flux decreases when we are having the beam propagate more within to the material. So basically it makes sense to define a kind of like a absorption coefficient or kind of term alpha. That's the kind of sigma, the absorption cross-section, and the population difference Ng minus Ne, that's the absorption coefficient. So basically we are taking this term here and we are equating that as an alpha term. And now in the case that we have more electrons within the ground state than within the excited state, this is a kind of essentially giving rise to decaying photon flux, so that it would make sense to call this absorption coefficient. In the case 2, we have reached population inversion. So we have this condition for the populations, so that the population of the excited state NE is larger than the population of the ground state NG, and this results in the case that the photon flux actually increases as a function of propagation length Z, and now we can define that the alpha is similarly like this, but now it's a positive quantity, so we can write that that's actually a gain coefficient. Since in general the absorption cross-section sigma is proportional to the line width function G, the absorption and gain, of course, they depend on the frequency. So please remember at all times that this is what happens, that all of these are frequency dependent parameters and quantities. And in addition, gain coefficients also depend on the broadening mechanisms that is really predominant in the medium. So this is something that we must take place. So like these coefficients, they really depend on the medium and what is the environment, and that kind of dictates, like in terms of the kind of frequency response of the math. Let's now look at the actual population dynamics and not just the kind of steady state case. So let's see what happens when we are like relaxing the restriction of just looking at the steady state case. And now if we start from the case of absorption being a dominating process, and this we can further assume that we have a pumping optical field that is strong, so that the photon flux F is larger than unity. The upper state population dominates, the NG is larger than NE, we have absorption. I think I would really rephrase this. So I would really say that the kind of like ground state population dominates. So I will be changing this into the notes. Sorry about this confusion. And now we can write the rate equation for the system. So now we are looking at the kind of population dynamics, and we can simply write what happens for these different two populations as a function of time. So we can write two differential equations. The first one for the population at the excited state, and this is essentially the rate of absorption or emission, and that depends on the population difference. And then we have a kind of spontaneous emission. So basically we have relaxation of the excited state, and this tau here is the kind of spontaneous characteristic time of the material. And this is basically the kind of population difference. Then we have a similar kind of rate equation for the ground state population. So we have W, NE minus NG. So now we don't have the minus sign. So that's different. And unlike in the previous case of excited state, we don't have a possibility of going anywhere lower. So we don't have any spontaneous emission processes taking place for the population of NG, the ground state. So here tau is the effective lifetime associated with the spontaneous and non-radiative decay channels of our gain medium. Now we can introduce a parameter to simplify the math. So we can introduce a population difference, delta N, that's defined by NE minus NG, and that's also known as the population inversion. And this is really the kind of parameter of interest in our course, because it really dictates, do we start having lasing or not? And we can write now the equation for its behavior, kind of go into the math forward. So the time difference or time derivative of population inversion, delta N, is basically the kind of difference of time derivatives of the excited state and the ground state populations. And using the fact that the total population is constant, so essentially we are not kind of like lifting electrons away from our two-level system, the total population N tot equals the population at the ground state plus the population in the excited state NE. And now we can write the time derivative of the population inversion, that it's essentially time derivative of the difference minus time derivative of the NE term, and we can then plug in the values of these terms. So this is what we get out by solving the previous equations or plugging them into this equation. And now we can write that everything is of this form. So basically we are taking use of the previous equations and we can write it into this form, so that basically the population inversion depends on our pumping and also depends on the actual kind of population inversion, and then depends on the total population and depends on the spontaneous emission rate. So that also matters here. Now let's consider a steady state case. So if this time difference of the population inverse is 0, we can really write that the population difference, the population inversion delta n equals n tot divided by 1 plus 2w tau. And recalling that the rate of absorption can be really written that it's the sigma times f, the photon flux, and that the photon flux can be written using the intensity divided by h bar omega. We can write the above expression really in a simple manner, so that the population inversion delta n equals total population divided by 1 plus I divided by saturation intensity, where this saturation intensity is being written that it's the h bar omega divided by 2 times sigma, the cross-section, times tau, the characteristic time. And this really shows that we have this kind of quantity known as a saturation intensity, I sat, and that the saturation intensity as such is really a property of the medium, and it's being inversely proportional to the sigma tau term here. So please take a while to think what this means and try to remember this. So really, the saturation intensity doesn't really depend actually on the kind of impinging field intensity, but rather it's really purely a material parameter telling to us how easy or how difficult it is to saturate this gain medium. And the main parameters of interest here are the absorption cross-section. So essentially, how easily can we have light being absorbed into the material, and then also the lifetime of this transition. So if we, for example, have shorter lifetime here, you can see the implications it has for the saturation intensity. And similarly, what happens if the absorption cross-section is being changed? That right away we can see that it has implications on the saturation intensity, and then also on the ease or difficulty of having the system to be on the kind of populated, having the system population inverted or not, or can we have lasing or not. This is really a fundamental equation. You should remember where this saturation intensity, how it depends on sigma and tau. This is really useful equation when you are trying to understand how lasers work. Okay, so now we can plug in these things into the absorption coefficient. So the absorption coefficient alpha is given essentially by sigma times delta n. So we can plug in all the values, and this is the kind of equation we get. And we can simplify this further so that the kind of absorption coefficient basically can be written that it's the alpha naught. So that's the absorption coefficient when we are having a weak pump hitting the substance, and that's divided by 1 plus I over I sat. So this kind of saturation term. So alpha naught is absorption cross-section under a weak pumping case. So this is basically a very fundamental and very important equation. So we see that when we have a weak pump, the absorption coefficient is whatever, and then when we are increasing the intensity, we are starting to see saturation effect. So it's not as easy to absorb light into the substance anymore. And we see that the absorption coefficient is really inversely proportional to the incoming intensity. And this is, like I already said, gives rise to saturation effects. At strong pump intensities, when the intensity is larger than the saturation intensity, we really have a case that delta n approaches 0, so that then we have roughly the same populations, and this means that really don't have absorption anymore. So that's the kind of really limiting case for absorption coefficient. And this physically tells us that we have a kind of induced transparency within the media, so we have a vanishing of absorption. So this, for example, happens when we just pump harder and harder into our substance, and as long as it doesn't break down due to a kind of stronger intensity, this is what will happen. And please note that this saturation of absorption, it's not just a kind of something that happens on this ultimate limiting case, but it's something that becomes visible already at lower intensities. So it's really something, a phenomena that must be taken into account basically all the time when we are looking at the kind of laser dynamics and lasing action. So this is really important kind of property or a feature of lasers. Now we can look at the math, and we see that the saturation intensity corresponds to the intensity of the pump, for which the absorption coefficient decreases by a factor of 2. This is basically arising from the mathematics, just now said out loud what it means. And we can now start generalizing our treatment by asking that how inhomogeneity of the medium affects things, how it affects the absorption. And now we can consider first the case of a homogeneous broadening. And now what happens is that saturation happens identically for all of these atoms. So this is what happens in the case of only having homogeneous broadening taking place within our medium. And what this means is that homogeneous line shape is being preserved when we have saturation effects, because all of the atoms, they behave the same way. So basically the kind of saturation just reduces the overall strength of absorption, but it doesn't change the line shape. So let me repeat, the absorption strength is uniformly reduced at different wavelengths. So this is what's happening when we have homogeneous broadening. And extremely interestingly, and I really ask you to think about this, and if you don't get it, talk with us during the discussions. This is really important. If the absorption line shape is inhomogeneously broadened, the situation is extremely different. So now what happens is that each atom contributes differently to the overall line shape envelope, and now each atom has a different saturation intensity because each omega naught primes vary per object, and only those absorbing objects that actually hit the right resonance, they will saturate, and the other ones will not saturate. And this is really fundamentally different from the case of a homogeneous broadening, and this gives rise to a phenomenon known as spectral hole burning. And this is actually extremely important in terms of real practical lasers. I'm trying to clarify this further with this picture because this is a really important situation to understand and a really important piece of physics to understand when understanding lasers. So first, let's consider the homogeneously broadened medium. So what happens is that all of these atoms that form my gain medium, they have the same line shape. And now in the original case, where I have a weak incident field, the line shape is having a different strength. So the absorption coefficient is the kind of original alpha naught. And now I increase the saturation, I increase the intensity. And when the intensity is equal to the intensity saturation intensity, then what happens is that the strength of the absorption just goes down, but it doesn't change the line shape. And ultimately, I can go all the way down into this induced transparency regime, but the line shape is not being changed at all when we are considering only homogeneously broadened media. And this situation dramatically changes when we are considering a case of inhomogeneously broadened medium. And now what happens is that this overall line shape function I'm drawing with the blue solid line here, it's actually a kind of like a composition of many atoms being absorbing my impinging field. So for example, in a gaseous medium, I have these different velocities and then I have different resonant frequencies accordingly. And now what happens when I'm impinging with a given frequency and I'm having a saturation effect here, we are only saturating a tiny portion of all the atoms. So we are only changing locally the line shape function. So we are having this kind of hole burning taking place here. And all the rest of the atomic emitters are really unchanged. And they can really still be absorbing light. Or respectively, when we are trying to make gain happen, they can still have a non-zero gain here, and that can give rise to detrimental effects, such as, for example, spontaneous emission, amplified spontaneous emission, ASE. Let's consider a case what happens when we are treating the gain in the system. So let's, for simplicity, consider a 4-level system. That's the easiest scenario to consider. And this is the energy level diagram for a 4-level system. So we are pumping electrons from the ground state into the energy state 3, we have a non-radiative relaxation. We have the quantum defect there, heating the substance a little bit. And then we have these two laser transitions, the excited state labeled with 2. And then we have the kind of like a number 1 state here into which the electrons are exciting. And now stimulated emission happens within this energy interval here. So this is our like a 4-level energy system. Now the population inversion, of course, must hold. We are considering a Gain system. So delta N equals, in our case, N2 minus N1. This must be greater than 0. We need to look at the rate of change of N2. That's, of course, what we would want to be looking at, but it's far easier to look at just the population inversion, delta N, because in a 4-level system, the level 1 is practically always empty. And that's the beauty of using a 4-level system and not a 3-level system. So essentially, the population inversion delta N equals to N2, or is very closely to N2. And now we can write a differential equation for the population inversion. So that's basically just using N2 here, the population of the excited state of 2. So we have the pumping rate. We are exciting electrons all the way from the ground state into level 3, and then we have this relaxation. So this process is giving us the pumping rate in the equation here. And then in addition, we have the stimulated emission taking place. So W times delta N, and then we also have a kind of spontaneous relaxation from the state within to the lower states. So basically here, this N2 divided by tau corresponds to spontaneous decay to here, first state, and also to the ground state. So that's the kind of term here, and this is basically dictated by this process here. So we have this kind of rate equation. Rp, like I mentioned already, is the pumping rate. Looking at the steady state case, so when delta N is constant, the population inversion, we have a situation that the Rp minus W delta N minus delta N divided by tau equals 0. That arises from the fact that if we are under steady state, then the time derivative of this delta N equals 0, and then we can solve this with respect to the population inversion delta N, and we have this kind of equation for the delta N. We can write, as in the previous case, for absorption, and by introducing the intensity through W equals sigma F. This is always what we have been using before, so that the W, the absorption rate, equals to sigma times I divided by h bar omega. And this results that the W tau equals to sigma tau I divided by h bar omega, and this we can again define that this is actually the intensity divided by saturation intensity, and here the saturation intensity for gain is essentially very similar to the case of absorption, so we have h bar times omega divided by sigma tau. So we can write that the population difference, population inversion delta N equals to the pumping rate Rp times tau divided by 1 plus I over saturation intensity. So essentially we can write that the line function is of this form. Line function is the absorption or stimulated emission cross-section times the population inversion. So we can write it simply in this way. And again, we can define that we have the kind of original weak pump line function G naught here, and that's been affected. So basically that will be saturating due to the fact of increasing pump. So what we have here is that we have I gain, and that's basically 2 times of I absorption. So the gain also saturate, but at higher intensities than absorption. And then we have characteristic parameters here that tell us that we have unsaturated gain case, so G naught. So that would be the gain when we don't have really an incident pump or the pump is weak. And then we have the saturation intensity, I sat, that really is dictated by the properties of the medium. Like I already emphasized, that's important. Please remember what is the equation for the saturation intensity. And here this picture shows what happens in practice in terms of gain saturation. So now we are having a weak incident pump, we have population inversion enough, and we have a kind of like a weak case pump gain. And what happens is that when we are increasing the incident pumping intensity, the gain doesn't actually increase at all, but rather it will be saturating, so lowering and lowering and lowering its value. And then ultimately, actually, we don't have that much of gain anymore in the systems at all. So this really changes how the laser behaves when we are cranking up the power. So we want to have more power out from the laser. We are having a stronger pump, but we don't get a kind of like linear dependence anymore for the output pump by increasing the intensity pump. And finally, let's now study how the gain is being influenced by different line broadening mechanisms. So for a purely homogeneous broadening case, if the saturation intensity or the intensity divided by saturation intensity equals unity, the gain drops to a value of half of its original value. And if the intensity is far larger than the saturation intensity, so that these equality holds, non-equality holds, we have a case where the gain is visibly decreased due to saturation effects. So really it's important now to understand that we necessarily always have these saturation effects in our system. And importantly, when we have a case of inhomogeneous broadening, then we have a similar phenomenon as in the case of absorption. So we have spectral hole burning starting to take place. And this is awfully often the case when we are dealing with gain media. So most of the time we really have inhomogeneous broadening, and this really affects how the lasers behave. So lasing frequencies might experience too low of a gain to overcome the lasing threshold and then contribute to the lasing action within that like a narrow frequency interval. But other frequencies can experience relatively strong gain, and these can really end up a kind of like harmful buildup of noise. And this is known as the amplified spontaneous emission, so ASE noise. And this is actually extremely important when we are looking at kind of like real lasers and real amplifiers, so that this amplified spontaneous emission noise is really many times kind of like ultimate killer of the performance of this instrumentation. So this is what I wanted to say to you during this lecture. And now I conclude that we are done with the second chapter on our course on laser physics. So what we have next is that we will go to the third chapter. So we'll switch gears a little bit, and we won't be talking that much about the kind of like a atomic physics. We don't be talking that much about the kind of absorption stimulated emission, but rather we will look into the kind of like a cavity aspect of making a laser. So we will be looking at passive optical resonators and how they can be engineered to make lasers. But I will thank you now. I will stop here, and please follow me when we are going to introduce to you the upcoming chapters and lectures within our course of laser physics. So thanks and bye-bye.